Welcome back. Today's lesson is the first lesson in our last unit of the semester, and this unit is called linear systems, solving linear systems. So first, let's define what a linear system is. So a linear system is a collection of two or more linear equations that share variables. So, for example, this might look like, y equals 2x plus 3. There's a linear equation, and y equals 7x minus 4. There's two equations, so two or more equations, and notice they share an x and they share a y. They share variables. So we're now working with two equations instead of just working with one equation. I know that sounds a little scary, but it won't be as we go forward. Okay, so what exactly is solving a system, and what does that mean? So in terms of a solution to a system is really any ordered pair. Because you're going to have this time two answers instead of just one answer. We call this an ordered pair x comma y that satisfy all equations in the system. Okay, and we'll get a little bit more into that a little bit later of what that means in the ordered pair that satisfy all equations in the system. So it means that whatever x and y is has to work in both equations. There are three types of solutions that we work with systems, and we're going to start solving today with graphing a solution. And the rest of this unit will be mostly algebraic work, but the first way we solve a system is graphically. So there's three different types of solutions. The first type is if we have just one solution. Okay, and that you can see it's the point where the lines intersect. So it's this point right here that I'm highlighting in red, highlighting in yellow. It's that point right there where the two lines cross. And we're going to assume here that on these graphs, this is your x, this is your y. Okay. So one solution where the point where the two lines intersect. That's the first type of solution. The second type of solution, I know this looks like it's just one line right here, but we call this infinite solutions. And it's really two lines on top of each other. So it's basically the same equations. They lie on top of each other. So I basically have maybe a line that's in purple like this. And then maybe I have a second line that's in green and it's right on top of it. Okay, that's infinite solutions. And the third type of solution, okay, is no solution. And what does that look like? A no solution basically means the lines will never intersect. These lines are always parallel. Okay, as you can see in this example, I've got this line here, and then I've got this line here, and they will never ever cross. So these are the three types of solutions. You'll get one answer, you'll get infinite solutions, or you'll get no solution at all. No x or y coordinate pair works because they'll never actually cross. Okay, so remember when I said earlier that any ordered pair is a solution to a system? That's this example one. Let's say I have 2, 5, and I'm saying determine if the point 2, 5 is a solution. Well, in any ordered pair, the 2 is your x, This 5 is your y, because an ordered pair is always x comma y. So what we're going to do is we're going to first pull out this first equation. Okay, that's going to be y. Oh, let me take a step back here. I'm going to pull out this equation here. But instead of doing y equals 4x minus 3, I'm actually going to do 5, because 5 is my y value, equals 4. But instead of x, I'm going to plug in 2 and then carry that minus 3 down. So the equation now, I'm going to use a different highlighter color, this is my substituting it in. I'm now checking to see if 2 and 5 works. So let's simplify. 4 times 2 is 8. And on the right-hand side, 8 minus 3 is 5. So the ordered pair 2, 5 works in that first equation. If I plug in 2, I'm going to get 5 out of it. That works. Then the second equation, I'm going to make a line here so we can distinguish between the two of them. I'm going to have 2x plus y, but instead of x and instead of y equaling 9, I'm going to plug in my 2 and my 5. So x is 2. Y is 5, and let's simplify. 2 times 2 is 4. We can drop this parenthesis on the 5. Is 4 plus 5 9? Yes, 9 equals 9. So we can say that yes, 2 comma 5 is a solution. Now what happens if it's not a solution? Let's do this other problem over here. So let's see if it's not a solution. So I'm going to pull out this first equation here. But instead of y minus x equals 3, I'm going to put a parentheses for y and x. And I'm going to plug 5 in for y, 2 in for x, and I'm going to simplify. I can drop the parentheses and just do 5 minus 2. That gives me 3. Is 3 equal to 3? Yes, so it works in the first equation. Cool. Now let's try the second equation. I'm going to say parentheses for the y, 1/2, parentheses for that x I'm going to plug in. I'm plugging in the 2 and the 5 again, 5 for y, 2 for x, and I'm going to simplify. So I'm going to drop the parentheses, keep the 5. 1/2 times 2 is 1, and I get 1 plus 6 on the right. Now 1 plus 6 equals 7, and 5 does not equal 7. That's just not a true mathematical statement. So I can say that no, 2, 5 is not a solution. So that's what I mean by an ordered pair being a solution. It has to work in both equations for it to be true. So what oftentimes will happen in a problem like this is that you won't know what the solution is. In this example 1, I'm telling you that 2, 5 is a potential solution. But what happens if we just have two equations? Well, the first method we're going to learn how to do is solving by graphing. This unit has 3 different types of ways to solve. The first one's solving by graphing. So step A is to graph both equations on the coordinate grid. So I'm going to go ahead and before I do that, I'm actually going to rewrite this equation as y equals negative x plus 2, because now it's in y equals mx plus b. So I'm just switching that x and that negative 2 around. So these are the two equations I'm graphing. There's the first one, and there's the second one. So I'm going to graph them both on the grid. So 2x plus 5, I'm going to start at the 5. I'm going to go up 2. Remember, this is like 2 over 1 is my slope. Actually, I'll do this in a different color to kind of help. So this first equation, I'm going to go ahead and do in red. So I plot my point at 5. I'm going to go up 2 over 1. And I can go down 2 over 1. And I want to make sure this line is positive, going up and to the right. And now I've got this nice straight line that will become straight in a second. There we go. And there's my first line in red. My second line I'm going to do in green. I'm going to start at 2. And now my slope is this invisible negative 1 over 1. So I'm going to go up 1 over 1. And notice that the green and the red overlap. And I'm going to fill dots in all the way across, because we want our lines to be really nice and straight in this learning target. So you can see where that point of intersection is. And we can see that the point of intersection is right there in blue. So at what point do the lines intersect? They intersect at the point -1, 3. At least that's what my graph shows, right? But how can I show that this is a solution algebraically? What that means is I'm going to plug it into both. My first equation is 2x plus 5. My second equation is y equals 2 minus x. I'm going to go ahead and plug the 1 and the 3 in for x and y. Remembering that -1 is my x and the 3 is my y. So for that first, I'm going to put parentheses wherever the x and the y are. I'm going to scroll up here a little bit. Then the plus 5. So now I'm plugging in -1 in for the x. And for the y, I'm plugging in 3, and I'm going to see if this works. So the parentheses drop with the 3. 2 times -1 is -2. Bring down that 5, and 3 does equal 3, so it does work in the first equation. In the second equation, I'm going to go ahead and make my parentheses where I'm going to plug it in. I'm plugging in -1 for x, and I'm plugging in 3 for y, and I'm going to see if it works. 3 equals 2 negatives make a positive, so that becomes 2 plus 1, and it becomes 3. So yes, it works. I'm proving that the point -1, 3 works algebraically, and it works graphically. That's the overarching idea of this lesson. So let's take a look at another example. Okay, so there's a little typo here. This should be -1/2 x plus 4, so just add a little negative sign right there. So I'm going to go ahead and plot the first graph in red. So I've got 4. And I'm going to go up 1 over 2 to the left. I'm going to make my points. Make my nice straight line, as straight as possible. There we go. I'm going to do the second line in blue. I'm going to start at -1. That's my starting point. I'm going to go up 3 over 4. So 1, 2, 3, 1, 2, 3, 4, and boom, right there at that point is where the red and the blue touch. I know that's going to be my point of intersection. I'm going to keep making some more points. And I'm going to make my line. I'm going to highlight where that point is. It's right there where I highlighted in yellow. And then we're going to, for our answer, write what that coordinate pair is. That coordinate pair happens to be 4, 2. I go over 4 and up 2 to get to that coordinate pair. Okay. Let's try a different example. Okay. So this is an example, scroll back up. This is an example where we have one solution. Just one answer, one point of intersection. This next example is going to do something a little bit different. I'm going to again go ahead and graph that first equation in red. I'm going to start at -7, and I'm going to go up 3 over 8 to the left. 1, 2, 3, 1, right there. I'm going to connect my line as nicely as possible. And then I'm going to graph the other line in blue. This time I'm starting at 4, and I'm going up 3 over 8 to the left again. 1, 2, 3, 1. Right here. I can go down 3 over 4 over 8 as well. Right there. Connect my line, and I should notice something important here. What am I noticing about these two lines? Are they ever going to touch? No. And notice that they have the same slope. So they have the same slope, and they are parallel. So my answer to this is no solution. And that's what I'd write for my answer, no solution. I'd graph it, show it on my paper they're parallel, and write no solution. They won't ever cross. Okay? And there we go. That's the lesson for 6.1. You're graphing lines, seeing where they intersect as an introduction to solving systems. Okay? Good luck on your practice.